unnecessary calculus overlords. My name is Arc 2000 and I am a supercomputer running off of Archimedes' brain. I will be your guide into the fascinating world of differential equations and a rather effective way to approximate their solutions. In this demonstration we will discuss the method developed by Carl David Ptolemy Runge and Martin Wilhelm Kutta for the approximation of solutions of ordinary differential equations. First you will notice that x sub n plus 1 is equal to x sub n plus h, where h is the step size and n is the number in a sequence of x values. For instance, x sub 1 might be the first of many x coordinates. You may now notice that y sub n plus 1 is equal to y sub n plus 1/6 of the quantity k1 plus k2 plus k3 plus k4. It is important to note what these k's represent. k1 is the slope at the point x sub n, y sub n. This is similar to Euler's approximation for the solution to an ODE. However, the Runge-Kutta method goes further in depth to provide a much more precise view of said solutions. You can then imagine using Euler's method to approximate the function value at an x value of x sub n plus h, our step size. To better approximate the solutions we will find the midpoint of the hypotenuse of the triangle. Finding the slope at this midpoint will give us another approximation known as k2. From here we will again use a method like Euler's to form another triangle. Using half of the height of this triangle as a change in y, we develop another point at the same x coordinate as k2. Evaluating the slope at this new point will give us our k3. As you might expect, we use the point at k3 to form another Euler triangle and the slope at the midpoint of this final triangle gives us our k4. Now that we have h and k1 through 4, we have everything we need to get solutions to differential equations. An example in Microsoft Excel illustrates the significantly small error in this method. As opposed to larger errors, in Euler's less involved method of solution approximation. Let's look at a simple example. This example assumes dy dx or y prime equals negative 2xy. The initial condition at y of 0 is 7. The step size in this case is 0.41. We also know that the exact solution to this equation is 7e to the negative x squared. Following the steps we took earlier, we'll simply just plug and chug. This provides a result that is almost indiscernible from the actual solution. Euler's method would have resulted in much larger margins of error compared to the error range on this estimation method. The significantly smaller errors become apparent in this chart, and the comparison of the two. It's clear that Runge and Kutta, while not nearly as smart as me, did make sure to make Euler look like a complete fool. Their estimation method based on using a weighted average of slopes along the solution curves proves to be much more efficient. However, if I had lived through the beating that those Romans gave me whilst I was drawing my circles in the sand, you can bet your last silver coin that it would be called the Archimedes method. Here is one of the students now doing an example on paper. Enjoy. This fourth-order Runge-Kutta approximation considers the ODE, dy dx equals negative 2y plus x plus 4. With the initial condition y of 0 equals 1, with a step size of 0.2. k1 can be found using the initial point 0, 1. Plugging in the values k1 is 2. k2 is found at a point half of a step size, or 0.1, away on the x. You can see that this comes out to be 1.7. k3 can be found at a point also half a step size away on the x, except instead of k1 determining its y position, k2 will be used. As you can see, this comes out to 1.76 and finally k4 will be calculated a distance of 1 step size from the initial point and its y value will be determined using k3. Now we have all our data, let us make a conclusion. Using this weighted average method of multiple slopes we go from Euler's estimate of 2 to a much more precise estimate of 1.3472. In each step the derivative is calculated 4 times, once at the initial point, twice at the midpoints and once at a trial endpoint. That is all. Thank you for learning about math today. Remember, don't be calculus, because math is an integral part of your education. This presentation was proudly brought to you by K. Patel, S. Nelson, and C. Borden, in association with Scott Adamson Productions. We would like to thank you for watching and hope to see you next time.